This is the agenda for today. First of all, I will tell something about the history of Paleis Het Loo. Then I will go into some aspects as key highlights, key challenges, the key innovations, the key takeaways, and at the end we will have the question and answer session. Paleis Het Loo, in 1684, stadtholder Willem III and Princess Mary bought a small castle Het Loo in Apeldoorn, and they had a new summer residence built next to the castle, which was to become Paleis Het Loo. Willem and Mary had Paleis Het Loo extended when they became King and Queen of England, Scotland and Ireland in 1689, and they transformed it from a modest summer residence to a royal palace. So after Willem and Mary, the Dutch royal family kept the Loo as their summer residence. The last residence of the palace, Princess Margriet and her family, left in 1977. From that point, the palace transformed into a museum and was opened in 1984. The goal of the latest round of alteration started in 2018, and it is to bring the palace closer to its original 7th century state and expand the exhibition facilities with an underground extension. So here you can see an overview from the air of Paleis Het Loo. In the middle you can see the space making in 2018 to make the underground extension, and this gives you a good overview of the palace as it was in 2018. Some key highlights. WSP is part of a technical design team alongside with an MIP building, physics and fire consultant, and we are working with the award-winning Dutch architect Kaan Architects on this project. The team of WSP consists of a core team of 6 people, and at a moment in time when we did the technical design, the team expanded until 25 persons. The Paleis Het Loo, the project consists of 5,000 square meters underground extension and 20,000 square meters of renovation. The palace is located in Apeldoorn. It's about 100 kilometers from Amsterdam in the Netherlands. The service provided by WSP are structural design and engineering, BIM coordination, and construction management. The execution of the building pit started on the 1st of January in 2018, and the underground extension, the execution started in June 2019. In this period of time, the building was commenced, and reopening is phased from April this year, and the last part will be opened in 2023. Then the key challenges from Paleis Het Loo. From a technical point of view, we had a discontinuous groundwater level over the entire site with a 50 centimeter of difference between the east and the west side. The second one, that we were building adjacent and underneath the 7th century listed monument, whilst the existing buildings themselves are the most valuable assets of the museum. The museum always tells us that they have about 70,000 artifacts which can be displayed in the museum, but they only have one building, and that's the most valuable asset. Without the building, they wouldn't have a museum. Third point is the pouring of 4,000 square meter underwater steel fiber reinforced concrete in 48 hours. Checking the existing buildings on temporary foundations was complicated as well. And the last key challenge was the coordination of 2 contractors with separate contracts but with joint interfaces. First of all, I'm going to tell something about the discontinuous groundwater level. On the left side, you can see the plan of the existing palace, and in red, you can see the underground extensions. On the right side, you can see some numbers about the groundwater table that we find during the time we did the soil investigations. We did cone penetration tests, and we also determined the groundwater table at different levels. And as you can see on the east side, the right numbers, there we had a higher water level than on the west side at the blue numbers. And the water was divided in between the green. I can show it, this green part over here. That meant that was a defining line between the high and the low groundwater level. At first, we thought it was due to the latest ice age in the Netherlands. In that period, the glaciers came all the way to Apeldoorn, and by pushing the ground layers forward, the horizontal layers were positioned vertically instead of horizontal. That's common in this area. You can find a lot of these systems working in the area. So we thought maybe it's the case here as well. But after excavating the building pit, it seemed that it was not a clay layer which was positioned vertically, but it was just a sand soil which was closed by iron oxide, which was transported by the groundwater, and during time created a barrier for the groundwater as well. And the key challenge, building adjacent and underneath the existing buildings. On the left side, you can see a three-dimensional model of the existing palace. And on the right side, you can see the floor plan again. And in red, there's the underground extension. As you can see, there are 5 parts on which the new underground extension is connected underneath the existing buildings. So 2 on the south side, on the left and on the right. The 1 in the middle on the right side, and 1 on the north side underneath the oldest building of the oldest part of the palace. We did have to make an excavation of 10 meters to build the underground extension, and this was also 8 meters below groundwater level. The maximum displacement of the existing buildings were defined by 2.0 millimeters. Here you can see the making of the cutter soil mix. It's an embedded retaining wall made by this cutter, who is mixing the soil with cement, and that it will become as hard as concrete, not as high quality, but quality enough to have enough stiffness and strength with the steel beams inside to be strong enough to keep the forces from the existing buildings and the ground layers at the right position. This cutter soil mix wall is 70 centimeters wide, and it was also in the reference design we made for the contractor. So the contractor did not change the design as the design WSP made for this part of the building pit. And here you can see the next phase after making the cutter soil mix. We excavated for the first part, and then there were tension anchors horizontal, and they were pre-stressed, and the pre-stressing was needed to minimize the displacement of the embedded wall. On this slide, you can see the making and the drilling of the vertical tension anchors, which are needed to keep the underwater concrete and the basement underground. So they have to take the forces of all the water pressure against the basement and against the building pit. Here you can see some photos of making the building pit from inside the existing buildings. In the reference design, we made this jetkraut walls, which are basically made by making several columns in the ground, which are overlapping and forming a wall. The jetgrouting is columns are made by drilling a lens into the ground whilst injecting grout under high pressure. In this way, a column is formed, and the lands can be brought back to the higher level again, and then make a new column. And by overlapping them, we made a wall. On the right side, you can see the horizontal drilling installation for making the horizontal anchors, just as we made them from the big building pit. We did not have enough room, so they were made while positioned outside and drilling through the windows on the right positions in the building pit underneath the existing buildings. So here you can see the excavation from the building pit underneath the buildings on the south side. So here you can see a good picture from the jet shroud columns made from inside of the building. These are the rough columns you can see over here, and you also can see the marking of the ground layers after excavating. So you can see they're not very straight columns with a definite dimension, but are a little bit bulky. You can see in front also the tension anchors, which were made in the building pit as well. These tension anchors are needed to keep the underwater concrete in place, and also needed to connect the basement, which has to be made inside the building pit to take all the water pressure forces and which can develop underneath the basement. In this picture, you also see the steel structure which was needed as a temporary foundation for this building. You can see here the steel beams, which are on which the walls of the existing building are supported by jacks. The jacks are these small parts over here, which can be seen a little bit in yellow. And the existing buildings were jacked on this temporary steel structure by displacement, so not by force. So it's a very fragile structure. It's the medieval masonry, so it cannot have too much deformations, otherwise it will crack and you get a lot of damage. So up front we made some calculations of the load division of the existing buildings and defined which load should go to which jack whilst checking the building on the temporary steel structure. So it was very, how do you say, they checked the building by making only small deformations, about 0.1 millimeter at a time. And then when you register only little pressure on the existing jack, then you take this jack out of the system and you only put extra force in the jacks who still can deform a bit with extra counterforce. So in this way, the total load of the existing building was transformed to the temporary steel structure with only 0.2 millimeters of deformation of the existing building. In this picture, you can see the making of the building pit on the north side, underneath the oldest part of the palace. As you can see, we did not have enough height here because of the masonry used in the old building. In the other parts of the building, we were able to demolish the first floor of the existing building, so to create more height, to make vertical tension anchors and also make good excavations. Here we did not have this height, so here was another technique used by the contractor. He used ground injections. These are bulbs injected into the soil, and by these bulbs overlapping in the soil, you can create walls and a floor which is made of chemical injections. And this can also be excavated after making these bulbs into the ground. You can see the man drilling now one of the holes. These are positioned in a right angle to develop and to inject a bulb about 6 or 7 meters underneath this working floor. So it's a very precise job, and it's very specialist work. So you for sure need a contractor who has done this before, because it's very difficult to design these kind of building pits without the knowledge of the contractors in the Netherlands. Now I can show you a little movie about the pouring of the 4,000 square meters of underwater concrete. It's a steel fiber reinforced concrete, and it was poured in 48 hours. There's no sound to this movie because the project manager is only telling something in Dutch. That's quite not understandable for most parties joining this webinar. So here you can see we are pouring the underwater concrete. You can see the water inside the building pit. These are the divers needed to pour the underwater concrete. So they lead the ducts and pipes in which the underwater concrete like this one is brought down. And they also prevent a lot of loose ground layers in between the underwater concrete and the soil mix walls, because you have to have a good connection, because otherwise you have a leakage. So all these connections are cleaned by divers as well. So it has to be a continuous delivery of concrete with steel fiber reinforcement. The steel fiber reinforcement was put in place at location, so not at the producer of the concrete. It was put into the mixers in place, and we had to close the underwater concrete in 48 hours. And especially we poured the underwater concrete from the east side to the from the west side to the east side, because we wanted to pour the underwater concrete against the water streaming of the groundwater, because otherwise, as I told you earlier, there were two regimes of water tables. So by excavating the division layer between the high level and the low level, there was a possibility that water would flow from the east side to the west side. So that gave the possibility or a risk that the underwater concrete would be washed away. So that's the reason why we poured the underwater concrete from the west side to the east side. As you can see here now the project manager is standing on the smallest building pit. It's interesting to know that we made one big building pit from underneath the square of about 5,000 square meters and 5 small building pits underneath the existing buildings. And we made walls in between them to reduce risk involvement, because when you have leakage in one of the building pits, then the complete building pit will be filled with water. So there was a too big risk for the client. We said, okay, we cannot afford this kind of risk. So we divide the big building pit and make 5 small ones. So if there occurs a problem in one of the smaller pits, which are quite difficult to make, then the work on the other building pits can continue, so they don't interact with each other. Then the challenge, as I told earlier, this is also a jacking of the existing buildings. This is the largest part of the existing building on the east side, which was jacked onto an existing steel structure. And because we had to remove the first floor also to make room to make the building pit, this steel temporary framework was installed into the existing building as well, as part of the temporary steel structure to be able to make the building pit and to stabilize the existing building. Here you can see a photo after the building pit was finished underneath the existing building on the east side. Again, you can see the jetgrout columns which were made, so you can see also the form. These are the cutter soil mix walls. So as you can see here as well, this wall was closed first, and then we made openings in between, and these parts of the cutter soil mix walls were deliberately used as a temporary foundation for the steel structure as well. So here you can see the steel beams with the yellow jacks in between, and this steel beam gives its load to these elements and this element. So here you can see the big building pit after the building pit was combined and connected to the small building pits. So over here you can see the holes which were made into the cutter soil mix. Also over here, and also you can see here that this wall was also demolished. So we get an open building pit from the big side, also underneath the oldest part of the building. This introduces also a new key challenge because the building pit was contracted by an integrated project delivery. So the contractor had also the responsibility to do some design work as well, together with WSP. And the contractor who is making the basement, the concrete basement, has a regular contract for the Netherlands. So he does not have to design anything. As you can see here, there's a lot of interaction. In this phase, the building pit was delivered to the second contractor, and the first contractor was only on the project to keep the existing buildings on the jacked structures and to keep the building pit dry. In this next slide, you can see we have on the left side, you can see the 3D model we made from Revit, and then you can see the interaction on the left side. You can see the 3D model in the status when the building pit was transformed to the second contractor. And on the second and third model, you can see the steel work which has to be made by the second contractor, also for the renovation works of the existing buildings. So it's quite hard to make these buildings and also have this amount of temporary steel whilst having two contractors and separate contracts. So we made these 3D models, and we made construction phases to determine which part of the work should be done by which contractor. So in the contracts we use 3D models, and even after in the construction phase itself, we made some more detailed drawings. You can see on the right side. Then we divided all elements which have to be made or works that have to be done. We divided it into 42 phases and 42 steps to realize the structure as it should be in the end phase after execution, the renovation, and the underground extension. So this was quite comprehensive, and it took a lot of planning and a lot of discussions also with the contractor, because we had to determine it for both parties the same phasing methods. Then the key innovation for this project. So I think in Dutch perspective, the contracting of two contractors with interfaces to optimize risk management. I think that's an innovation we used here, because we did a lot of detailed engineering and also spent a lot of time and effort in the phasing of the different structures, for most of all underneath the existing buildings. Then the key takeaways. So what did we learn from Paleis Het Loo? Design-wise, I think it's important to have an eye for building practices and protection of the existing historical buildings when integrating new construction and renovation. And the second one is agree with authority at an early stage about compliance with the building regulations for the historical buildings. For instance, in the Netherlands, it is when you have an old building and you don't change the use of the building, then you don't have the necessity to make new calculations, because it's a right that you own by having a building permit from the past. Then you can still use the same building and not comply with the latest regulations. So for a monument, it's very important that you don't change too much, because it demolishes the historical value of the building. So we had a lot of discussions with the authorities about how can we define the structural analysis so that we can lower the amount of works we have to do to get the structure right again. Then the phasing and conditions. It's very important to ensure different contractors to understand the necessary construction process. So for this project, it was in very much in detail. The second point is to integrate the expertise of contractors in special techniques in the design, especially here for the building pit. We use the knowledge of the contractors to get that into the design as well. That's also the reason why the first building pit contractor had a different contract than the contractor for making the basement. And I think that's the only way to design this in a proper way, because if you don't do this together with a contractor, then you have to work on execution documents like the jacking in very detail. And then you still have the risk that when the contractor comes on board, that he will change some things, and then you have to start designing again. So it's better to have the contractor on board before the end of the design and design it together in a proper way so that it can be executed. A third point is that it's very useful to find a balance between practical aspects and technical precision. So not everything can be calculated. So some things and matters might be better to get a practical solution and not trying to solve it all by calculations. And yes, that is it. The last part is that the use of the 3D model helps creating a good insight in phasing the construction. As I've shown earlier on one of the slides, we made a 3D model and also use different phasing to get more insight in the aspects of phasing of the construction and all risks involved in this phasing. And in the end, best for project, guiding the project, I think it has to be done by best for project through partnership and collaboration. I think we have succeeded in this project by collaborating with the contractors for the building pit to make a building pit which was delivered in time and without deformations of the existing buildings, and also without damage of the existing historical buildings. So now we're at the end. So now it's time for the Q&A.
Thank you, Eddie, for your presentation. We just have a few minutes for the Q&A. You can download the PDF version of this presentation from the handout box. And if you have more questions, you can ask them in the question box on the GoToWebinar platform. I will start with the first question regarding the divers. What do the divers do when pouring the underwater concrete?
That's a good question. I tried to say something more about it. So the divers, they will lead the pouring of the concrete. So they use a hop-dobber system to get the concrete at the right level under the water, and the divers have to lead these tubes to the right place to get the concrete on the right place. And they also have to clean all connections between the underwater concrete and the temporary structures of the soil mix walls, because otherwise you get some sand enclosed between the concrete and the wall, and that only will lead to leakage after pumping the water out. So that are the activities that the underwater divers do. And the one thing I've forgotten to mention, so I will tell it now. The divers also mount the anchors on the anchor plates on the tension anchors for the underwater concrete. So when the anchors are bored or drilled into the building pit and excavated, then you only have an anchor, but that should be connected to the underwater concrete as well to take all the water pressure from underneath and lead it into the anchors again. So all these steel plates are mounted by the divers as well.
Perfect. Thank you for clarifying this. The next question is, how are the acceptable deformations for the medieval masonry determined?
that we did on some documents we use in the Netherlands. So you have hogging and sagging for existing masonry. And we tried to make calculations, but it's very difficult to get it into a model because you almost need to have some big parts of the existing masonry cut out of the walls to test them and to say something about the E-modulus and also about the stresses and the strength of the masonry. So that was not possible. So we used a lot of information, and we did a desk study about what kind of deformations are acceptable for all buildings. And we defined a relative rotation of 1 to 600 for hogging and 1 to 300 for sagging.
Thank you. I will take the last question. Why did the team didn't choose the steel sheet piles instead of the current solution?
That's very simple, because sheet piles are not as stiff as a soil mix wall with steel beams inside. So it's with steel sheets, we could have done it on strength, but the deformations of the sheet piles would be too high. So horizontal deformations leads to also vertical deformations of the existing buildings, and leads to too many deformations and possible damage of the existing buildings.
Thank you. So we're at the end of our webinar session. Please feel free to follow up directly with Eddie via the contact details shown on the screen. And I would like to thank all attendees for joining today. Thank you very much for your time. And thank you, Eddie, for a fantastic presentation. Very interesting. Thank you.